Right now, somewhere in the Iranian desert, in the ancient city of Yazd, there are buildings keeping their residents cool in 110 degrees heat. They have no air conditioning units. They have no electrical wiring. They have no moving parts of any kind. And some of them have been doing this continuously for over 800 years. What nobody knew, or rather, what the modern world chose to forget, is that ancient civilizations cracked the code on cooling centuries before anyone dreamed of compressors and refrigerants. They did it with wind, water, stone, and geometry. Their systems worked so well that some of them are still outperforming modern air conditioning today. And we didn't abandon them because they stopped working. We abandoned them because something came along that let us stop thinking altogether. This story doesn't start with a machine. It starts with the desert itself and the first people who figured out how to make it livable. Picture the Nile River Valley around 1500 BCE. The Egyptian sun is relentless. Temperatures in the open desert regularly push past 115 degrees Fahrenheit. The sand radiates heat back up at you. There's almost no shade, and the Egyptians of the Old Kingdom didn't just survive in this environment. They thrived in it. They built one of the most advanced civilizations in human history, and they did it without a single watt of electricity. Their cooling secret was almost comically simple. They hung wet reed mats over their doorways and windows. That's it. Wind blows through the wet reeds. The water evaporates, and the evaporation process pulls heat out of the air. The breeze that enters the room on the other side is measurably cooler than the air outside. Evaporative cooling, the same principle your body uses when you sweat, turned into architecture. And it wasn't just reed mats. Egyptian builders oriented their homes and temples to catch prevailing northerly winds off the Nile. They used thick mud brick walls that took hours to heat up during the day, keeping interiors cool well into the afternoon. Wealthier households had servants sprinkle water on stone floors, letting evaporation pull heat from the room at ground level, right where people sat and slept. These weren't random habits. They were a coordinated set of cooling strategies embedded into everyday Egyptian life. They also used porous clay jars for their drinking water, a technology so effective it's still used in parts of rural Egypt and India today. These jars weren't glazed on the outside, so tiny amounts of water would seep through the clay walls and evaporate on the surface. The evaporation draws thermal energy from the water inside, cooling it down. The water inside the jar stayed noticeably cool even when the air outside was blistering. No ice, no refrigeration, just the physics of evaporation and the right choice of material. Archaeologists have found these jars, called seers, in tombs and household ruins across the Nile Valley. Some date back to roughly 2500 BCE, 2,000 years ago. An Egyptian potter figured out that leaving the outside of a water jar unglazed would keep the water inside cold. We spend billions of dollars a year on refrigeration technology, and they solved the drinking water problem with clay and patience. I mean, think about that for a second. And if that were the only ancient cooling system, it would already be impressive. But what the Persians built makes the Egyptian approach look like a rough draft. Travel east from Egypt to modern-day Iran to the city of Yazd. This place sits at the edge of two deserts, the Dasht-e-Kavir and the Dasht-e-Lut. The Lut Desert holds the record for the hottest surface temperature ever recorded on Earth, over 159 degrees Fahrenheit. Yazd is right next door to that. It is, by any reasonable standard, one of the harshest places on the planet to build a city. And yet, people have lived there continuously for over 5,000 years. The city is one of the oldest on Earth. And the reason it works, the reason anyone can survive there at all, comes down to two pieces of engineering that most people have never heard of. The first is the Bechger, which translates roughly to wind catcher. Walk through the old quarter of Yazd and you'll see them everywhere. Tall, rectangular towers rising above the rooftops, some of them 40 feet high with openings near the top designed to catch even the slightest desert breeze. These towers have interior partitions that create separate channels. Wind enters through the openings on the windward side, gets funneled down through these channels and is pushed into the room below. That alone would provide decent ventilation. But the Persians didn't stop there. They combined the Bechger with an even older piece of infrastructure called a Kanal, an underground network of water channels that runs beneath the city and across the desert. The Kanal system is an engineering marvel in its own right. Workers, called mukannis, would dig a series of vertical shafts into the ground along the slope of a mountain or hill, then connect them at the bottom with a gently sloping tunnel. Groundwater from the mountains seeps into these tunnels and flows downhill by gravity alone, sometimes traveling for tens of miles underground, arriving at the city cool and clean without a single pump. Yazd has a Kanal network that stretches across the entire region. Some of these tunnels running for over 40 miles, and the water inside stays naturally cool because it's insulated by the earth around it, typically resting at around 68 degrees to 72 degrees, regardless of what the surface temperature is doing, when the hot desert air gets pulled down through the batcher and passes over these underground water channels. The same evaporative cooling principle the Egyptians discovered kicks in, but on a much larger and more sophisticated scale. The result is that air entering the living spaces below can be 10 degrees to 15 degrees cooler than the air outside. In a city where the outside temperature regularly exceeds 100 degrees, that's the difference between misery and comfort, and it runs 24 hours a day, 7 days a week with zero energy input, no electricity, no fuel, and barely any maintenance beyond occasional cleaning. The wind does all the work. What comes next is the part that still doesn't make sense to most modern engineers. Some of these systems in Yazd have been operating for over 800 years. 8 centuries of continuous climate control with no replacement parts, no software updates, no service contracts. Try getting 8 years out of a modern HVAC unit. The Persians also developed the yakhchal, which is essentially an ancient ice factory. These are massive dome-shaped structures with walls up to 6 feet thick, built from a special mortar that insulates against heat. They used the cold nighttime desert air and shallow pools of water to make ice, actual ice, in the middle of the desert. They stored it in these dome structures, and it would last through the entire summer. Ice cream in the Persian Empire wasn't a fantasy, it was a Tuesday afternoon. Now, while the Persians were engineering wind and water in the desert, the Romans were taking a completely different approach on the other side of the Mediterranean. And their solution was, in some ways, even more elegant. For a while, the Roman approach to cooling actually seemed simple. Wealthy Romans built their homes, their domos, around a central open courtyard called an atrium. The atrium had an opening in the roof called a compluvium that let in light and air. Below that opening sat a shallow pool called an impluvium that collected rainwater. Fountains often ran in or near this pool. That didn't last as just decoration though. The whole system was thermal engineering disguised as architecture. The courtyard created a stack effect. Hot air rises and escapes through the roof opening, which pulls cooler air from the shaded ground-level rooms into the center of the house. A constant gentle circulation. No fans required. The fountains and pool added humidity to the air passing through, which dropped the temperature further. And the whole structure was shaded by the building itself, so direct sunlight rarely hit the courtyard floor. Everything the Romans built worked against them if you looked at it from a modern architect's perspective, because modern architects designed buildings to keep outdoor air out. The Romans designed buildings to move outdoor air through, but the real genius was in the walls. Roman construction used thick stone and concrete, materials with high thermal mass. During the day, these walls absorb heat slowly, keeping the interior cool while the outside temperature climbs. At night, when the desert or Mediterranean air drops by 30 or 40 degrees, the walls release that stored heat back, warming the interior. The walls basically act as a thermal battery, smoothing out the wild temperature swings between day and night into a comfortable, stable indoor climate. If you've ever walked into an old stone church on a hot summer day and felt that immediate wave of coolness, you've experienced exactly what the Romans engineered on purpose. Now, the Romans could have stopped there. They didn't. This approach wasn't limited to individual houses. Entire Roman cities were designed with thermal comfort in mind. Streets were oriented to channel prevailing breezes. Public buildings used massive vaulted ceilings that let hot air rise far above the occupants. Bathhouses used underfloor heating called hypocausts in winter. and relied on the same thermal mass principles for cooling in summer. And this wider approach to climate-responsive urban design wasn't unique to Rome. Across the Middle Eastern and Mediterranean world, civilizations arrived at remarkably similar solutions through trial and error over thousands of years. Walk through the old Medina of Fez in Morocco, or the ancient streets of Seville in Spain, or the historic quarters of Damascus in Syria. You'll notice the same patterns repeating everywhere, and the temperature difference between these old neighborhoods and the modern parts of the same cities is striking. You can literally feel it on your skin. The streets are so narrow that the buildings on either side shade the walkway for most of the day. In some old quarters, residents strung fabric canopies between buildings to block the remaining slivers of direct sun. Walls and rooftops are coated in whitewash or light plaster that reflects sunlight instead of absorbing it. A whitewashed wall can reflect up to 80% of the solar radiation hitting it, compared to a dark surface that absorbs almost all of it. That's a massive difference in how much heat enters a building. Inside, ceilings are high in every room because hot air rises and you want it as far from the occupants as possible. Windows and doorways are positioned on opposite walls to create cross-ventilation, so breezes flow through the building instead of stagnating. Interior courtyards with plants and water features add moisture and shade to the center of the home. Thick exterior walls, sometimes 2 or 3 feet deep, provide the same thermal mass buffering the Romans relied on. These weren't accidental design choices. They were accumulated wisdom, refined over generations by builders who understood their local climate the way a sailor understands wind. Each building was tuned to its environment, and when you stepped back and looked at the whole city, it functioned as a single interconnected cooling system. The urban fabric itself was engineered to manage heat. And this is where the story could have ended, a simple celebration of ancient cleverness. If every civilization that came after had kept building this way, you and I would live in very different cities right now. By the early 1900s, the world was changing fast. Electricity was spreading across American and European cities. Factories were mechanizing everything from textile production to food processing. And in 1902, a young engineer named Willis Carrier was working at a printing company in Brooklyn, New York, called the Sackett-Wilhelms Lithographing and Publishing Company. The company had a problem, and it had nothing to do with keeping people comfortable. Their problem was ink. Humidity in the factory was causing the paper to absorb moisture, which made the ink misaligned during color printing. Pages were coming out blurry and unusable. Carrier's job was to figure out how to control the humidity, not the temperature. He designed a system that passed air over cold coils to condense the moisture out of it. The air that came out the other side happened to be cooler and drier. Carrier had stumbled onto mechanical air conditioning almost by accident. He didn't set out to cool people. He set out to dry ink. Over the next few decades, the technology spread, slowly at first and then all at once. Movie theaters were among the first public spaces to adopt air conditioning in the 1920s, and they advertised it heavily. Theaters would hang banners outside that read refrigerated air and cool inside. The phrase cool comfort became a marketing slogan. Summer blockbusters exist partly because theaters were the coolest buildings in town during July and August, so people flocked to them just to escape the heat. Then came the post-war housing boom. By the 1950s, window air conditioning units were becoming affordable for middle-class American families. Builders in the American South and Southwest, regions where people had historically built homes with deep porches, high ceilings, and cross-ventilation to manage the heat, started putting up tract houses with low ceilings, small windows, and no porches at all. Why design for airflow when every house comes with a window unit? Air conditioning didn't just change buildings. It changed entire demographics. The population of the Sunbelt states exploded in the second half of the 20th century. Cities like Phoenix, Houston, Las Vegas, and Miami grew from modest towns into sprawling metropolises. None of that growth would have been possible without mechanical cooling, and the entire culture of building design shifted alongside it. This is the detail that would come back to haunt us. Once architects knew they could rely on mechanical cooling, They stopped designing buildings that worked with their climate. Why bother orienting windows for cross-ventilation when you can seal the whole building and pump in cold air? Why build thick thermal mass walls when thin glass curtain walls look sleeker and cost less? Why design narrow shaded streets when you can build wide boulevards lined with reflective glass towers? The sealed glass box became the default template for commercial architecture around the world. The same office tower design that works in Seattle got copied to Phoenix, to Dubai, to Singapore, to Lagos. It doesn't matter that Phoenix hits 115 degrees in summer and Seattle barely cracks is 80. The buildings look identical because the architect doesn't need to care about the local climate anymore. The HVAC system handles everything, and so does the electric bill. Think about it this way. For thousands of years, architecture was fundamentally a conversation between the builder and the local climate. Every choice, the thickness of the walls, the direction the windows faced, the height of the ceilings, the width of the streets, was an answer to a specific environmental question. Air conditioning ended that conversation. It told architects they could build whatever they wanted, wherever they wanted, and the machines would handle the consequences. That's an incredible amount of freedom. It's also an incredible amount of arrogance. If you're wondering how that's even sustainable, so is everyone else. Air conditioning now accounts for roughly 10% of all global electricity consumption. In the United States alone, Americans spend about $29 billion a year on the energy to cool their buildings. During summer heat waves, air conditioning demand pushes electrical grids to their breaking point, causing brownouts and blackouts. And the refrigerants used in most AC systems are potent greenhouse gases, some of them hundreds of times more effective at trapping heat than carbon dioxide. So, we replaced ancient systems that ran on wind and water with modern systems that run on fossil fuels and leak chemicals into the atmosphere. And the irony is that our modern cooling systems are literally making the planet hotter. Which means we need even more cooling, which makes the planet even hotter. It's a feedback loop that the Persians and Romans and Egyptians never had to worry about because their systems didn't produce waste heat or emissions at all. The glass skyscrapers of downtown Houston and the mirrored towers of Dubai are, in a very real sense, uninhabitable without constant electrical power. Cut the power to a sealed glass building in a hot climate and it becomes a greenhouse within hours. The windows don't open, the ventilation shuts down. The thermal mass is negligible because the walls are mostly glass. The building was never designed to be livable on its own. It was designed to be a shell that machines keep habitable. Compare that to a house in Yazd, Iran, that has kept its residents comfortable for 800 years without a single power outage because it doesn't use power. When a heatwave hits Yazd, the badgers keep working. When a sandstorm knocks out a transformer, the qanats keep flowing. The system doesn't care what the electrical grid is doing because it was never connected to one. We traded resilience for convenience. And the old systems didn't fail. We just forgot how to value them. And the encouraging part of this story is that we're starting to remember. In 1996, an architect named Mick Pierce completed a building in Harare, Zimbabwe, called the Eastgate Center. It's a mid-rise commercial and shopping complex in a city where temperatures swing between hot days and cool nights. Pierce didn't install a conventional air conditioning system. Instead, he studied termite mounds. Termite mounds in Zimbabwe maintain a nearly constant internal temperature of around 87 degrees F, even when the outside temperature swings from over 100 degrees during the day to below 50 at night. The termites achieve this through a network of tunnels and vents that constantly circulate air, opening and closing channels to regulate airflow as conditions change. It is essentially a living, breathing building that the termites have been perfecting for millions of years. Pierce designed the Eastgate Center to mimic this approach. The building has a series of fans in the lower levels that draw in cool nighttime air, which gets stored in the concrete floor slabs and walls, the same thermal mass principle the Romans used 2000 years earlier. During the day, as the building warms up, the heat is vented through chimneys in the roof, while the stored coolness in the concrete keeps the interior comfortable. The warm air rises and exits through the top. Fresh air is drawn in through the bottom. The cycle repeats. The result is a building that uses roughly 90% less energy for cooling than a comparable conventional building. Its tenants pay about a tenth of the cooling costs they would in a standard office tower. And the building doesn't need a massive mechanical cooling plant on the roof, which saved so much money on construction that the developers scooped the design investment in the first few years. 90% less energy. Not 10%. Not even 50%. 90%. That's not a marginal improvement. That's the kind of number that makes engineers rethink everything they assumed about how buildings should work. And the Eastgate Center isn't alone anymore. Across the world, architects and engineers are rediscovering what they now call passive cooling, a term that makes it sound like cutting-edge green technology. When really, it's the same set of principles that humans used for thousands of years before Willis Carrier's ink-drying machine changed everything. In Masdar City, Abu Dhabi, planners studied the traditional wind tower neighborhoods of the Persian Gulf and applied those lessons to a brand new development. Streets are oriented to funnel cool breezes from the surrounding desert, and buildings are clustered close together to shade each other during the hottest hours. The same approach used in the Medinas of Morocco and the old quarters of Damascus. A modern wind tower in Masdar's central plaza stands nearly 140 feet tall and pulls nighttime breezes down into the pedestrian streets below, dropping the temperature at ground level by as much as 68 degrees Fahrenheit compared to the surrounding desert. In parts of India, architects are reviving the jali, a perforated stone screen that filters harsh sunlight while allowing air to pass through freely. The jali creates a dappled, diffused light inside the building and generates a gentle draft as air moves through its hundreds of small openings. This technique dates back to Mughal architecture in the 16th and 17th centuries. But contemporary Indian architects are now designing jazi screens using computer modeling to optimize the size and placement of every perforation for maximum airflow. Ancient craft meeting modern computation. In southern Europe, where summer heat waves have been breaking records year after year, new residential developments are being designed with thick insulated walls, shaded courtyards, and cross-ventilation built into the floor plan from day one. They look a lot like updated versions of the Roman domus, because functionally that's exactly what they are. Even in the United States, the concept is gaining traction. The American Institute of Architects has been pushing for what they call climate-responsive design, which is really just a formal way of saying build like people did before air conditioning made everyone forget. Cool roofs that reflect solar radiation instead of absorbing it, light-colored exterior surfaces that bounce heat away, strategic window placement to create natural ventilation pathways, thermal mass in floors and walls to buffer temperature swings. All of it is ancient knowledge dressed up in new vocabulary and backed by new data. The architects who design these buildings aren't reinventing the wheel. They're digging up a wheel that got buried when cheap electricity made lazy design profitable. The windcatcher towers of Yazd, the evaporative reed mats of Egypt, the thermal mass walls of Rome, the shaded narrow streets of Fez and Seville. Every single one of these techniques has a modern equivalent that engineers are now scrambling to integrate into new construction, because the old way of just blasting cold air with fossil fuel-powered machines is becoming too expensive, too fragile, and too destructive to continue. There's something worth sitting with in all of this. For most of human history, the smartest people in the room were the ones who paid the closest attention to the room itself, the direction of the wind, the angle of the sun, the temperature of the ground beneath their feet. They built cooling systems that lasted for centuries because those systems didn't fight nature. They cooperated with it. Then, for about 100 years, we decided we didn't need to pay attention anymore. We had machines for that. And now, with energy costs climbing, grids straining, and the climate warming faster than the models predicted, we're circling back to the same principles that a Persian builder in Yazd understood 800 years ago. The most advanced cooling technology on Earth might already be sitting on a rooftop in the Iranian desert, quietly doing its job while the modern world finally catches up. What survived from those ancient builders wasn't just stone and mortar. It was proof that the most durable solutions are often the ones that don't need a power outlet, and that working with your environment will always outlast